Okay guys, let's do some work with vectors to see finding the angles between them. So to find the angle, we have that equation from above. Cosine theta equals the dot product divided by each vector's magnitude. So for u and v, we have cosine theta equals the dot product of u times v over the length of u times the length of v. So the dot product is, of course, multiplying the piecewise components. That's 3 times -4, which is -12. -1 times 0 is 0. 2 times 2 is 4. Divided by each of the lengths. So how do I find the lengths of these? I square all of the terms. And so let's see, the length of u is the square root of 9 plus 1 plus 4, because 9, that's the square root of 14. The length of v is the square root of -4 plus 0, -4 squared, so 16 plus 0 plus 4, that's the square root of 20. Now, technically, square root of 20 is 2 square roots of 5. So if I take square root of 14 times 2 square roots of 5, I'm just going to write that here. I can simplify from here. That would be -8 over 2 square roots of 70 is cosine theta, which means theta is the cosine inverse of -4 over the square root of 70. I'm going to reduce. You can also put -8 over 2 squared root of 70. It's not going to do anything. If you do that inverse, you get 2.07 radians, or 118.56 degrees, which is consistent with what we said. If the dot product is negative, you should be between 90 and 180 degrees. I'm going to go ahead and put the lengths of v, oh, it's already over there, length of w and length of z over here. 1 squared is 1, 1 squared is 1, 2 squared is 4, add them together, that's 6, so this is the square root of 6. Z is the square root of 5. We'll just do one more of these. Let's do v and z. Now let's do the dot product of v and z. -4 times 2 is -8. 0 times 0 is 0. 2 times -1 is -2. Now the dot product, or the length, magnitude of v and magnitude of z is 2 square root of 5 times square root of 5. Well, we know what that is. This is -10 over 2 times 5, which is 10. So if cosine theta equals -1, it means theta is pi. That's because v and z are parallel. If you multiply z by a -2, you get v. Because it's a negative number, that means they're going in opposite directions, and we expect that means there's an 180-degree angle between them, or pi radians. Okay, other applications of the dot product. So depending on the information you're given, sometimes you want to rewrite that formula we just had. If you take those two magnitudes and multiply them to the other side, you'll get the dot product by itself. This can sometimes be useful, because in space, sometimes it's convenient to measure the angle between the non-zero vector v and the initial unit vectors, because we don't have a single direction to move to cover everything anymore. So we can take the angles alpha, beta, and this y as the directions and angles of v, which means there's 3 different cosines for the directional cosines of v. Like, what does that even mean? Well, it means in the x direction, we can talk about the angle between v and the angle of the unit vector in the x direction. Similarly, the angle between v and the unit vector in the y direction, etc. And why is this helpful? Because this dot product is equal to a v times the unit vector I. Using this formula, is just the length of v times the length of I times cosine alpha, We know the length of I is 1 because it's a unit vector. We have the length of v equals times cosine alpha total. Now we know the other way to interpret the dot product is simply the multiplication of components. Now v1, v2, v3 being the components of v times that, or the dot product times the unit vector in the x direction, which is 1, 0, 0. Only thing times 0 is 0, so the only thing that will survive this dot product is v1 times 1, which is just v1. What does that mean? If these two things are both equal to this dot product, they are equal to each other. So we get the length of v times cosine alpha equals the first component of the vector v. That means we can solve for cosine alpha and see that it's v1 divided by the length of v. And we can make that argument for v2 and v3 as well using the other two angles described above. As a result, we can make a unit vector in each direction. V is v1 over the length of vi plus v2 over the length of vj plus v3 over the length of vk. But we already knew this because we can divide each component by the length to get the unit vector. What do we know about v1 divided by the length of v? It's cosine alpha. Similarly for cosine beta and cosine, I think that's omega. Since this is a unit vector, the length is 1, which means cosine squared alpha plus cosine squared beta plus cosine squared omega is 1. Now find the directional cosine angles for the vector 2i plus 3j plus 4k. So there's an easier way to do this. We don't want to have to break this down every time up here. We want to use what we know. We know that cosine alpha is equal to our initial vector component divided by the length of v. I would rather use that. We know v is 2i plus 3j plus 4k, which means the length of v is 2 squared, which is 4, plus 9 plus 16. It's this square root, which is the square root of 29. What is my first term of v? It's 2, so cosine alpha equals 2 over the square root of 29, which means alpha is the cosine inverse of 2 over the square root of 29, which is 1.19 radians, or 68.2 degrees. So that tells you how far, really, from the x-axis this angle is. Okay, so cosine beta, same idea. We have the same length. It's just now 3 over the square root of 29 instead. 3 over the square root of 29. So that means beta is the cosine inverse of 3 over the square root of 29. So beta is 0.98 radians, or 56.15 degrees. We can do the same thing with omega, at least what I hope is omega. I'm not great with my Greek alphabet. Sorry. It's wrong, but it's this weird downward shaping fish symbol. This means omega is the cosine inverse of 4 over the square root of 29, which is 0.734 radians, or 42.03 degrees. Now you can check that the cosine of all of those squared is equal to 1, but I promise that it is, because it only makes sense with what they're equal to, that would be the case. Okay, so these are all applications of the dot product. We can talk about one last application of the dot product, and we'll do that in the next video.